In this lesson, we're going to talk about one of the more advanced concepts you can find in word problems on the executive assessment, rates and work. So, rates and work are all based off of one specific equation that work or distance is equal to rate times time. Now, you can also rearrange this equation to state that rate is equal to your work or distance divided by time, and your time can be articulated as the work or distance divided by rate. Now, your proportions are going to be constant as they relate. Now, that's only if the rate is listed as constant. This is one of the kind of cheaper tricks that the exam can deploy, which is if it doesn't say it's a constant rate, it might not be a constant rate, and Jimmy could theoretically do 30 widgets in 15 minutes and then just loaf off for the rest of the hour. So make sure that your rates are always listed as constant. Now, if your time is your constant, you know that your work and rate are directly proportional. So if you increase the amount of work that you do, you increase the rate at which you do it if the time remains the same. So, for instance, if you complete 20 units of work in 5 hours, your rate is 4 units per hour. But if you keep the same 5 hour time and increase the number of units from 20 to 40, your rate will double to 8 units per hour. Now, if you keep your rate constant and increase your work, your time will also increase for another direct proportion. So, if for instance you have 20 units completed at 5 units per hour, your time is 4 hours. But if you were to increase the number of units from 20 to 40 and keep the units per hour at 5, you would then have to take double the amount of time and 8 hours instead of 4 hours to complete the work. Now, if your work remains constant, you have an indirect or inverse relationship between your rate and your time. So when one goes up, the other must go down. So here, if we have 20 units of work that is completed at 5 units per hour, the time is going to be 4 hours. But if we keep the units at 20 units of work that are completed and we double the units per hour rate from 5 to 10, we have the amount of time it will take from 4 hours to 2. So you have to make sure you keep track of whether your variables will increase together, decrease together, or one goes up and the other goes down. So then let's take a look at a sample rate problem. So as always, you want to set up your scratchpad as normal, listing your answer choices vertically A through E. And in this case, we've got our answer choices listed, and they're simple numbers. So we got 4, 5, 6, 10, and 24. I'd write them out on the scratchpad. Then, of course, we skip to the end of the problem to identify the sought value and label the choices as such. So here we're being asked for how many more hours would it take those remaining workers to complete the order working at the same constant rate. So we're looking for the number more hours to complete the job that's being presented. So then we read from the beginning, taking notes and setting up calculations as we go. So 6 workers working at a constant rate at Bill's Widget Emporium are able to fill a certain standing weekly order for a number of widgets in 20 hours. So we know that the formula of work is going to be equal to the rate times the time. In this case, the workers stand in as the rate. So we know that 6 workers times 20 is going to be 120 units that are completed in those 20 hours abstractly. So now we need to solve for our new time, which is going to be the constant work divided by the new rate, which again is just articulated by the number of workers. So our new rate and new number of workers, we've been told, is going to be 5. So our new time is going to be 120 units of work divided by those now 5 instead of 6 workers. And our new time would be 24, but the more hours would, of course, be 24 minus 20, and 4 more hours for the correct answer choice of A. So this is the technical solving process for this problem. We will see this problem again in a moment. Now, you can also consider rates and work in terms of ratios, and there is a relatively handy ratio table you can use. So we're going to just consider proportions and ratios using the sample of a fruit basket. So we've got a little table here. We've got apples, bananas, and total fruit. We're going to assume that this is a sad winter fruit basket. There's nothing but apples or bananas in it. So using the table, the ratio values and the real values will sum to the total parts. And you always have to make sure that when you're building a ratio table, that your final column is your total of whatever you're counting. So in this case, we could have a ratio of 5 apples to 2 bananas, which means that the minimum number of fruit we could have in our fruit basket is going to be 7 pieces of fruit. But we don't know the actual real number values in our fruit basket just yet. But if we consider some real values as 25 and 10, we know that that's going to sum to 35, and that's just a simple multiple of the ratio that was presented. So your multiplier is going to be constant for all columns in any ratio table or proportion. And you can divide any real value by the ratio to find that constant multiplier for the table. So if we took, say, 35 and divided by 7, we discover that our constant multiplier here is going to be 5. And that's how we can work through the table. You can multiply the ratio value by the multiplier to solve for any of the real values. So you can multiply down to solve within a column and add across to sum to the totals. So let's consider that same problem we just saw using a proportional rate solving process. So we're going to pretend we've already read everything. We've set up the Scratchpad as we always do. And this time we've just got a little ratio table. So we've got our workers and our hours. So we know the ratio of workers to hours is 6 workers for 20 hours. But because we have our workers going down, we know that when you decrease the number of workers, that you're going to decrease your workers as the rate, you're going to increase the number of hours that it takes. So the fewer workers we have, the more hours it's going to take. And we know that our new total of workers is 5 because we're going to subtract a worker. So we can logically estimate first to eliminate any impossible choices. Clearly, it's not going to more than double the number of hours. So that's out. It's just going to decrease it by a little bit, not going to take a full double amount of time. So then we want to consider our constant multiplier. And we remember that you can divide the new total, the target, by the ratio to figure out what your multiplier is. And 5/6 is that multiplier. But because we have an indirect proportion here, you have to use the reciprocal to account for that indirect relationship. So that means instead of multiplying 20 by 5/6, we're going to multiply it by 6/5. And if you multiply 20 by 6/5, you can take your 20 divided by 5, you get 4. 4 times 6 is going to give me 24. And once again, 24 minus 20 is 4 more hours. So this just is a second way to solve the same problem using a little ratio table. And you can do this for many of these rate problems. But we're not yet done with how to solve these types of problems. We're going to introduce a cousin to the average circle you may have seen in another of our lessons, the rate circle. And this is just a physical manifestation of that rate times time equals worker distance formula. So we know that the worker distance is equal to the rate times time, and that's why the bottom 2 pieces multiplied together will give you the top piece. And any 2 values that you have within the circle can solve for the third. And you'll use multiple circles potentially to coordinate complex rates. And you can add or subtract the raw work, the distances, or the times, provided you have a constant metric. And this is another level of difficulty they can introduce. If one of your rates is in days and the other one's in weeks, well, you've got to make sure that they're all using the same metric of time. But you cannot just work through your rates across multiple circles unless you're combining them, in which case you may be able to add them. So this is a really handy and flexible way to work through some of your more complex rate problems that you might encounter on the executive assessment. So we've got our same problem again. So we still have set up everything. We know that we've got 6 workers and we've got 20 hours. And we've got a new target of 5 workers based on the problem. But we don't know our new hours. So you can note possible alternative tactic clues, such as the word certain. And we remember that certain means possibly we can plug in and model our own scenario. There's also an unknown value dictating the problem, that number of widgets that we don't know right now. So we can potentially model this with our own easy value and use that rate circle. So let's work on through this alternative approach for the same problem. You're going to set an easy total value for the unknown number of widgets in that certain order. So you can consider a product of the given values as an easy total. So we know that we've got 6 workers, 20 hours. So let's just say we've got 120 widgets, so 120 units. Your results will then be a given rate of 1 unit or 1 widget per worker per hour. Because if I've got 120 widgets to produce, I've got 6 workers doing it. That means it's 20 units per worker, and that's over 20 hours. So we've got 1 unit per worker per hour. This is the easiest model we can do for a rate circle. So we're going to set up a rate circle for the new rate of 5 units per hour, because now we lose one of our workers. So we just have to divide that 120 units or widgets by the 5 units or widgets per hour to find that 120 divided by 5 is once again 24 hours. And 24 minus 20 is again still 4. So there are 3 different ways to work this one rate problem. And flexibility in approach is really helpful with rates, because oftentimes it's just the sheer number of different variables moving, and the rate circle is probably the most forgiving way to organize things and potentially solve if you don't see an immediate direct approach, either using the proportions or just solving using the formula like we did in our first example with this problem. So there is one more thing that comes into play here with rates and work as well. That's combined time. And there is a formula for specifically combined time. And that's going to be the time for A times the time for B divided by the time for A plus the time for B will give you the time it will take the 2 workers to complete a job together. Now, this is just a simplification of the combined rates formula. But you have to make sure that the metrics are consistent so that you're doing everything in minutes, everything in hours, whatever it may be. Because if you switch minutes to hours and don't make sure that each of the times are in a consistent metric, obviously you'll get an incorrect response. But you have to make sure you deploy this only for combined time. It doesn't work for anything else. And really, it's a shorthand that works for one specific use case, but a use case that is frequently deployed enough that you want to know it. And do beware of applying this formula for combined rates or trying to apply a combined rate formula to combined time. You have to do this exact articulation of the algebra to expedite it in this fashion. But if you can use the combined time formula when it's applicable, it's a really handy way to work through a combined rate time question. So let's go ahead and move over to the whiteboard and take a look at how we might use that combined time formula with a sample word problem. So here we have a sample word problem solving question that you might see on the quantitative section of the executive assessment. And we've got simple numbers, so we're just going to write those out, and we'll make that a little bit bigger. But we've got 1/2, we've got 1, we've got 1.5. We've got 2, and we've got 2.5. And we skip to the end, and we figure out what we're being asked for. And we're being asked for in how many hours can a single standard photo order at Jabba the Photo Hut be completed if the 2 women work together at their respective constant rates. So we're looking for the number of hours for an order together. So we set this up first, starting at the beginning. We learned that Jenna and Bella are each available to print a standard order of photos at Jabba the Photo Hut. If Jenna can print a standard photo order in 6 hours, okay, so the time for J is equal to 6 hours. And then Bella can print the same standard photo order in 3 hours. So we've got, okay, time for B is equal to 3 hours. And how many orders can a single standard photo order at Jabba the Photo Hut be completed if they live right together? So we're looking for the combined hours together. So there are 2 distinct ways that we can work through this problem. We're going to do the technical first, but then we'll look at the other. So we remember from moments ago that when we have the combined time, we know that the combo time is equal to the time for A times the time for B all over the time for A plus the time for B. So let's apply this. So we know that the combo hours, that is going to be equal to Jenna's time of 6 hours times Bella's time, which is 3 hours, all over the time for A plus the time for B, which is going to be 6 plus 3 hours. So that, of course, is going to be 18 divided by 9, which is 2 hours. And you can see how quickly the combined time formula pays dividends here as we select choice D. Now, that said, we talked about how you may not recognize this, and not all is lost with a rate problem at all. So we're going to just show how to work through our rate circle alternative as well. So we're just going to build a little rate circle here to start. And we know that there's going to be a standard order of photos. And we're going to have a Bella circle. We're going to have a Jenna circle. And we're going to have a combo circle. So setting this up, everything is dictated by how many photos are in a standard order. I've got 6 hours and 3 hours. So it probably is the case that 6 times 3, 18 is an easy plug-in value. And it's not an accident that that shows up here. So we've got 18 photos as our photo order, as the work for each of the 3 circles. Now, then we know that Bella's time here was 3 hours, and that goes in the bottom right. And that's going to mean that Bella has a rate of just 18 divided by 3, which is 6 photos per hour. So 6 per hour. Then for Jenna takes 6 hours. And we do the same division to find that Jenna is going to produce 3 photos per hour. Then we can just sum the 2 rates because we know that when they're working together, they're able to do 6 and 3. So the combo rate, when they're both working together at their individual rates, is 9 photos per hour. And of course, if we divide 18 by 9, we discover that that gets us the exact same 2 hours as their combined time. So there is a lot of flexibility in the rate circles. If you can't technically address any individual work rate problem on the executive assessment, really think about these circles because they're quite handy to organize all the pieces. But of course, if you recognize that you can use the combo time formula here, that's probably the most efficient path to solving. So let's go ahead and take a look at one more example here of rates as it pertains to a sample data sufficiency problem. So we start with what we know, and we learned that Cam's Bicycle Bureau has received a production order for 300 bicycles. So we know that the PO is equal to 300. And we'll just write bikes. Can Cam guarantee that the order will be completed in 2 weeks or fewer? So will the time be less than 2 weeks? And so we can skim ahead and we see that we're being asked about days. So what we need is going to be, will the time be less than 14 days? And now that we know that the purchase order or the production order is 300 bicycles, well, in order to determine whether it will be done in 14 days or fewer, so less than or equal to, see, technically, we've got to determine as what we need is the rate. And of course, this is boxing off what we're being asked for. Is the rate going to be less than or equal to 300 divided by 14? Or if we do 14 into 300 here, 14 goes into 300 2 times, subtract out the 28. We then have a 20. We've got 1, and it's basically going to be 21.67 bikes per day. Because if we get over 21.67 bikes per day, then we know that we've reached the target rate for Cam's Bicycle Bureau. So condition 1 says that Cam's Bicycle Bureau can produce a maximum of 50 bicycles a day. So that means that the rate is less than or equal to, and we'll just have it as daily rate, is less than or equal to 50 bikes per day. So that includes the 21.7 bikes per day, but there's nothing stopping this from being 1 bicycle per day. We don't actually know what the rate is. We just know what the maximum is. So that by itself is not sufficient to determine definitively whether the rate is more or less than 21.67 bikes per day. So our options remaining, of course, are B, C, or E. Now, condition 2 says that the Bicycle Bureau produces a minimum of 25 bikes a day. So that means that my daily rate is greater than or equal to 25 bikes per day. And that, if we have what we need, guarantees that we're going to reach that minimum of 300 bikes in 2 weeks or fewer. And if you need to test it out, of course, you can just do 25 times R14. And if you do 25 times 10, you get 250, 250 plus 25 times 4, that's actually 350 as our minimum if you wanted to double check. And especially on the first half of the executive assessment, that might be an advisable step. So this is how you can address, again, one of the more complex concepts in some of the harder word problems that you might encounter on the executive assessment, probably in the second half of the quantitative section. Go ahead and practice some of these problems on your own to deploy all of the different approaches to maximize your possible efficiency and effectiveness with this type of question on test day.